Hello. In this video we show an example of operating a LFP battery with the ctrlX drive system, and how to run charging and discharging cycles using industrial ctrlX drive components. The modular ctrlX drive with shared DC bus offers energy efficiency and application flexibility, specifically the combination of regulated regenerative power supplies and DC-DC converters. Before we dive in, first some notes. This video shows a battery application in a demonstrator. For other use cases, please observe the ctrlX drive documents or consult with Bosch Rexroth. Overall, the specific battery application determines the ctrlX drive components and control. Let's look at how the battery system influences the ctrlX drive selection in this application. Topics like battery isolation monitoring requirements, ranges of voltage, current, power, etc., battery management system BMS supply, 12-volt, high voltage on-off function, CAN bus communication and state of charge data. Let's have a look at the relevant ctrlX drive components. Power supplies up to 100 kilowatts are offered with XVR and up to 4000 kilowatts with InverDrive ML. The DC-DC converter XMV has 80 ampere and 210 ampere capacity and can be operated in parallel mode. DC-DC converters with 400, 600, 1200, 2400 ampere and higher are possible with InverDrive ML. The XVR power supply converts energy between AC grid and the shared DC bus where the energy is exchanged with motor inverters and the DC-DC converter XMV. The XMV controls a DC output voltage so energy flows into the battery, charging it. When discharging, the XMV controls the DC output voltage so energy flows back to the DC bus and the XVR supply puts excess energy back into the AC grid. Let us have a closer look at the components and wiring of the DC-DC converter. The XMV is connected to the XVR supply via shared drive DC bus. The DC bus negative is the negative DC output of the converter, while the positive DC output is after the DC smoothing choke and capacitor. A high voltage transducer measures the DC output voltage and outputs a 0 to 10 volt signal to an XMV input, for fast 250 microseconds closed-loop regulation of the DC output voltage. If need be, the DC current can be measured with a shunt and second high-voltage transducer. Additionally, a filter and discharge circuit for the DC smoothing capacitor may be necessary. Finally, the DC positive and negative output must use DC contactors to connect the battery. Now we review the detailed functions of the DC-DC converter using XMV. At the left side, this WebHMI screen allows us to step through the converter functions. At the right side, we can see the status information of the XMV's internal states. In this state, the XVR supplied with 220-volt AC grid is already generating 400-volt DC bus voltage which is suitable to feed the DC-DC converter for charging and discharging the LFP battery. We also see that the DC-DC converter XMV is ready for operation. Let's review the steps required so the DC-DC converter will output the commanded voltage. In step 1, we switch the XMV power section to be ready for operation. Then in step 2, we get the XMV to the state, ready for power output. In this step the XMV will use the soft start function for voltage buildup. Our commanded voltage of 210 volts is now also output by the DC-DC converter. Closed loop regulated at 210 volts. So, next we can activate voltage control, here always active by default. Now we can connect to a battery, but first let us review additional details. Here's some steps that need to be executed in the demo controller. First, we need to read the actual voltage value over CAN bus from the battery management system BMS. Then the DC-DC converter XMV must be commanded in voltage control to output a voltage that matches the battery's voltage. Additionally, one should set low value limit for DC current and power in the XMV. This minimizes excessive DC current when closing the DC contactors and connecting the DC-DC converter with the battery. With DC contactors closed, we can adjust the XMV's DC current and power limits and command DC-DC output voltage to charge and discharge the battery. During operation, the system controller monitors the ctrlX drive system and battery management system BMS. Now let us use the demonstrator's HMI and operate battery charging and discharging. The left side HMI shows both the actual battery data and actual DC-DC converter data. Here we can set the DC charge voltage and limits for DC current and power. The demonstrator has a separate display that always shows us actual voltage, current and power of the DC-DC converter. A green arrow downward indicates the battery is being charged while a red arrow upward means the battery is being discharged into the AC grid. So let's run the demonstrator. First, we will activate the battery charge function. This step will power up the supply XVR, if not already powered up. It also sets the charge voltage to 2 volts higher than the actual battery voltage and sets the current limit to 3 amps and power limit to 6000 watts. We start the DC-DC converter and can see its output go to 212 volts, as commanded, 2 volts above the battery voltage. Then we switch the battery side DC contactors on. And then the DC contactors of the DC-DC converter. So now both DC systems are connected together. With the DC-DC converter command voltage higher than the battery voltage, the DC-DC converter is charging the battery, but limited to 3 ampere, the active current limit. We can now increase the current limit, for example to 23 ampere, and we can see the actual charging current and power increase accordingly. Please note that when we increase the current limit to 30 ampere for faster battery charging, we must also increase the commanded DC-DC output voltage, for example to 220 volt. Now we see that the battery's actual data increased but only to 213 volts and 28 ampere. The reason is that the demo's configured DC-DC converter power limit of 6000 watts is reached. The small difference of the power reading is based on the demonstrator's control design. 24-volt control power is supplied by another DC-DC converter connected to the battery voltage. Battery discharging can be achieved by simply lowering the charge voltage command to a value that is lower than the battery's active voltage, for example to 200 volts. Now we can control discharging power by simply adjusting the current limit, for example to 3 ampere. In automated production, typically various battery charge-discharge profiles are commanded to the DC-DC converter. In this demonstrator we use a normalized power demand profile generator, -100 to +100. The DC-DC converter commanded voltage is 220 volt for positive values resulting in charging, and 200 volts for negative values resulting in discharging. The value 0 to 100 equals 0 to 6000 watts. Test profiles can be generated by any application, for example, in a test computer or PLC. In this demo, a web HMI allows users to define normalized power profiles. The web HMI sends normalized profile data to the PLC program, where the data is adjusted to the demo's power capabilities and then commanded via EtherCAT to the DC-DC converter. So let us start a second instance of the browser, for example Chrome. We enter the URL address of the profile generator. The ctrlX core requires authentication, so if a message like this shows up, please choose Advanced and then proceed with logging in. The home screen shows the battery's status information. Next, we open the menu with the active power profile. Then, from the battery charge operation screen, we can start the active profile and can see the profile running. The profile command points are sent via OPC UA to the demos PLC for scaling with set limits and then commanded to the DC-DC converter. Under Settings, the demo user can enable profile controls and recipe management. Next we click on the icon for Profile Library and can select and activate a different power profile. Here is the newly selected profile running. The test computer can also receive and record command and status data. In this demonstrator we display recorded data with the ctrlX app, IoT Dashboard. In IoT Dashboard, we can choose the desired time scale. Here is a 5-minute recording of the normalized power commands. And 5 minutes recording of the actual battery charging current. So, this was a brief introduction how the DC-DC converter of ctrlX drive can be used for battery charging and discharging in production and recycling, battery power simulation, for example e-axle testing, and with other energy storage or buffers, for example, supercapacitors, fuel cells, and solar panels. For future reference, you can find here the ctrlX drive documentation and several subject-related how-to videos in the YouTube playlist of Bosch Rexroth US. Find all links posted in the text below this video. Join the ctrlX automation community to find further information and use the forum to post questions and inquire about DC-DC solutions. Thank you for your attention.